Hi, I'm John Ainsley, CTO from Doulos. In this video, I'm going to tell you how to run the easier UVM code generator in the context of EDA Playground. UVM stands for the Universal Verification Methodology for System Verilog. If you don't know what System Verilog is and you don't know what UVM is all about, you're probably watching the wrong video. Easier UVM from Doulos consists of a set of coding guidelines and an automatic code generator for UVM. Both the coding guidelines and the code generator are free and openly available on the web. If you're interested in learning more about easier UVM, I suggest you watch some of the other videos. Anyway, in this particular video, we're going to focus on running the easier UVM code generator in the context of the EDA Playground website. Before we dive into the details of running the easier UVM generator, let's start with a quick review of EDA Playground. The first thing you do is to choose which language you want to use, System Verilog in this case. Then you select your simulator, we'll choose VCS, and then you enter your design and test bench code. So the design code goes in the tabs on the right hand side of the window, the test bench code in the tabs on the left hand side of the window. You can enter the code either by typing it in directly or by copying and pasting or drag and dropping code fragments, or you can drag and drop an entire file into one of the windows and that will put the contents of the file into the window. In this case, we'll copy and paste our design under test, which is just an adder with two 8-bit inputs A and B and one 9-bit output F that captures the carry bit. Then you enter your test bench code into the tabs on the left hand side of the window. So I'll copy and paste in my test bench. So you can see the test bench here is just a simple piece of System Verilog code that instantiates our design under test and then has a procedure that creates a monitor and then generates some stimulus. And that's all there is to it. Now we can go ahead and run our code. So we hit the run button. At this point, you have to actually log in to EDA Playground. I'm not already logged in, so it's prompting me to log in. I'll hit Login Save Edits. And we have two choices. You can either log in with a Google account or a Facebook account. Well, I'm already logged into my Google account, so I'll just choose Login with Google. Now I'm logged in, I have to hit Run again. You can see the button at the top here is You can see the button at the top here has changed from run to a red stop button. Simulation runs, and in the region at the bottom of the window here, we can see the simulator log file. So in this case, you can see VCS running, and near the bottom of the log, you can see the output from the dollar monitor, with the input and output values appearing in the log file, which is showing that our adder is working. Now let's move on to easier UVM. The easier UVM code generator is going to generate the test bench for you. So UVM is a System Verilog class library that's used for building constrained random verification environments, and it turns out that much of the code in any UVM environment looks the same as the code in any other UVM environment. A lot of it is boilerplate code, and that code can be generated for us from the code generator. We'll also have to add some of our own code to do the creative work. This diagram shows all of the files that are used by the code generator. So on the left hand side we've got control files and DUT files that are read by the code generator, and then on the right hand side we've got the test bench code that's generated from the code generator. The control files are created in EDA Playground as tabs on the left hand side of the window, and the DUT files are created as tabs on the right hand side of the window. So if we take a look at the control files, we've got one interface template file for each interface to the design under test, a common template file that contains common settings, a pin list file that describes how the variables within the interface template files are connected to the ports on the design under test, the DUT files that represent our design itself, and include files that are also created as tabs on the left hand side of EDA Playground, and each of those include files contains a user-defined code fragment that gets included within the generated code. In order to run easier UVM within EDA Playground, we need to enable it through this checkbox. Before we check the box, it's a good idea to clear the Test Bench tab, and you'll see why in a minute. Now when we enable easier UVM, the tab on the left-hand side is replaced with a help file that gives you some more information on running the code generator within EDA Playground. Note if you want more information on easier UVM itself, you can get it by clicking the little eye icon next to the Enable Easier UVM checkbox. That will jump you to the full set of documentation and tutorials on easier UVM on the Doulos website. So let's start creating our easier UVM control files. The first control file that we're going to create is the common template file. So I click on the plus sign, then type in the file name, common.tpl. The common template file in this case is very simple. It simply needs to contain one setting, and that one setting identifies the name of the DUT module. So the one and only module in our design under test in this case is adder, so we've added the setting DUT top equals adder. That's our common template file finished. Then we add an interface template file for each of the interfaces on the design under test. Well, this very simple design under test will regard as having a single interface, an arithmetic interface. So we'll add one interface template file and we'll choose the name arith for the name of that interface, since we're going to be doing arithmetic through that interface. We then have a number of settings within this interface template file. So I'll copy and paste in those settings. Let's take a look at what those settings mean by relating them to the structure of the UVM verification environment. So this diagram shows the structure of the generated code for our simple example. If you don't recognize this diagram, you probably want to review some of the other videos in this series on easier UVM. Each of the boxes at the bottom of the diagram correspond to module-based code with the System Verilog interface and the module for the DUT itself. Each of the boxes at the top of the diagram correspond to UVM classes. So relating this to our interface template file, our agent name, arith, is used as the root name for the agent and all of the classes associated with the agent. So the agent, sequencer, monitor, driver are all going to have this string arith as part of their name. Trans item then corresponds to the type of the transaction class. So the code generator is going to generate a class called trans in this case to represent the transactions sent from sequencer to driver and sent out through the analysis port of the monitor. The trans vars then correspond to variables within that transaction class, or more strictly the sequence item class. So inside this transaction we've got two inputs, which are 8-bit numbers, and one output, which is a 9-bit number. The interface ports, or IF ports, within the interface template file correspond to variables within the generated System Verilog interface. So again here you can see the two 8-bit values A and B and a 9-bit value F. The name of the System Verilog interface itself is derived from the agent name, so you can see it's simply the agent name arith with the suffix if on the end. Then the next tab on the left-hand side of EDA Playground is going to be the pin list file. The pin list file is the file that maps the variables within the interface to the pins or ports on the DUT, and it's divided into sections. Each section consists of an exclamation mark followed by the name of the interface. So here we've got pling arith interface, and then each of the ports on the DUT, A, B and F, are mapped to the corresponding variable in the interface template file. And then you get multiple sections in the pin list file, one section for each of our interfaces. So now we'll add a tab for our pin list file. Click on the plus again, the file name is always pin list, and then we fill in the contents of the pin list file just as I've shown you. So we've got the arithmetic IF section and 3 connections to A, B and F. Do remember to put in a carriage return after the last line in the file. So now we're ready to go ahead and run. So I'm going to hit the run button, and when I hit the run button, it will first of all run the Easier UVM code generator based on the control files we've set up on the left-hand side. And then if code generation is successful, it will go ahead and run the simulation. Let's go for it. So we can see messages flashing by in the region at the bottom of the window. I'll expand this region a little bit. And now simulation is stuck. You can see that the stop button here is still red, but nothing seems to be happening. I'll explain what's going on in a few minutes, after simulation's finished. Let's scroll up and look through our simulation log. So you can see right at the top of the log, we're running the Easier UVM code generator script. Here you can see messages from the code generator telling us the version number of the code generator, and we can see where it's generating its files. Then we run up VCS. As we scroll down the log, we'll come across a set of messages that are created from a call to print topology. Here we are. Here's our UVM topology printed out. You can see you've got the usual UVM component hierarchy, a test instantiates an env, instantiates an agent, and so on. We can also check out the version of UVM that we're running a little higher up in the log. So we're running the version of UVM 1.2 that's built into Synopsys. Great, that's what we wanted. Then we go right down to the bottom of the log and we can see a red message telling us that we've reached the maximum runtime. What's happened here is that the simulation has got us stuck in a loop and has timed out after consuming 60 seconds of CPU time. The problem is that we haven't actually implemented our UVM driver or monitor. And in order to have a meaningful simulation, we need to complete our UVM verification environment by actually implementing the driver and monitor code that's going to wiggle pins on the design under test. And to do that, we're going to add some further user-defined code fragments into the tabs on the left-hand side of the EDA Playground window. This time we'll add those files by dragging and dropping the entire files into the window. So I click on the plus icon, and then instead of typing in a new file name, I'll simply drag and drop two files onto this screen. Here we go. So two new tabs have popped up, arithdriverinc.sv and arithdrivermonitor.sv. Let's take a look at these two files. So here's the code fragment that's going to be inserted within our driver. You can see it's a simple task which takes the values of the input1 and input2 variables from our transaction and drives them onto the A and B variables within the interface and then consumes some time. If we look at the code fragment that's going to be included within the monitor, that's another simple task that contains an infinite loop. Each time we get an event on the output of our adder, that is output F, then we're building a transaction, sending that out through the transaction port of our UVM monitor, and writing a UVM info message to the simulation log. Having added a couple of files containing user-defined code fragments, I now have to add a couple of additional settings to the interface template file to tell the code generator where to find those code fragments. So let me copy and paste in those two settings. So I've got a driver inc setting and a monitor inc setting with the names of the two include files. Now I should be good to go, so I'll hit the run button again. The code generator runs, then the simulator runs. Now simulation's finished, I can scroll back in the simulation log. I've got some standard messages that always come out from a UVM simulation. And then I've got a line of code from my monitor that prints out the message that I included in the monitor, that UVM info message. So I'll just take a look at the arithmetic monitor inc tab. So here we've got a UVM info that prints out A plus B equals F. So here we've got 175 plus 160 equals 335. So that's it, it works. I've actually run the code generator from a set of template files to generate a System Verilog test bench, and then run the System Verilog test bench with the design under test. It works, but we've only generated a single transaction, so we've only tested our design under test with a single addition. Suppose we want to generate a bit more stimulus. Well, there's a very convenient way of doing that by putting another setting in our common template file. One of the settings that we can add will adjust the number of transactions that's generated by the default sequence. So let's change it from 1, which is the default, to 8 and rerun our simulation. So now simulation is finished, we can scroll back, and here we see the output from the monitor as it receives each of the 8 transactions, and we can see that we've stressed our adder a little bit further. So good, it works. Let's just review the control files we used. So we started with the common template file. The common template file identifies the top level module of our design, and then we added a further setting to increase the number of transactions that were generated from the default sequence. Then we had an interface template file for our adder that identified the names of the various classes that were generated and also identified the variables within the transaction and within the interface. The pin list file that made the connections between the variables in the interface and the ports on the design under test, and a couple of user-defined code fragments, one for the driver and another for the monitor. If you want to see the actual generated code, you can get hold of that code by checking the box Download Files After Run and rerunning the code generator in the simulation. So as simulation comes to an end, it wraps up all of the files in the simulation directory into a single zip file and downloads that file to our local computer. So we can click OK to save the file. Then we can open the file from the downloads area in our browser. And here you can see within the zip file all the files from the simulation directory, including the generated TB directory. That's the interesting one. So if we go inside generated TB, we'll see the structure created by the code generator. We dive down further, we can take a look at the code generated for our agent. There's a particular example. Let's open up the driver code. So here's the driver for our arithmetic agent. You can see we've got some standard boilerplate code that's always the same for the driver, including a run phase method. And then at the bottom of the file, there's the user-defined code fragment that's been included within the automatically generated code. EDA Playground simulations have some strict limits on the number of lines of code and the simulation time. But the code generator doesn't have any limits, so if you generate a really large verification environment, you can still download it and simulate it locally on your own computer, even if you can't simulate it within EDA Playground. Now we've finished our run, we can save this example for later. So to do that, I'd hit the Save button, and then if I click on the button on the right-hand side that shows my username, I'll see a list of all my previously saved playgrounds. So here's the one I've saved most recently. You can see it's called UU8, that isn't very meaningful. It's much more useful if you actually name your examples. So back here in EDA Playground, I can fill in a name, adder, save it once more, go back to my area, and I can see I've now got an example named adder. I can allow anybody else to look at my examples by making them public. So as long as the public box is checked, anybody who can find your example will be able to see it. You can share examples deliberately through the Share button. This allows you to share your examples on social media. But to share an example, all you need to do really is to give somebody a link. The link is a simple URL, and anybody who knows that URL will be able to open your example and look at it, provided the example was public, provided the public box is checked. If you uncheck the public box, the example will still exist at that link, but nobody but you will be able to see it. So you have to be logged in as yourself in order to be able to see examples that are not public. So that's how you run Easier UVM on EDA Playground. Of course, there are many further features in the EDA UVM code generator, and you've got full access to all of those features within EDA Playground, so I'd encourage you to play with it and enjoy. Well, at Doulos, we deliver training classes worldwide. We can run classes in hardware design, hardware verification, SystemC, FPGA technology, ARM processor technology, and embedded systems. If you want to know more, do visit our website www.doulos.com and we'll be glad to help.